me start the recording. Yeah. Okay. Okay. As all of you know that there will be the second exam number 2 on October 25th. That will be next Wednesday. And again, it will be very similar to your exam number 1. It will be an open book / open notes, open digital devices exam. And please let me know if the time does not work for you. We'll try to find out a separate time for some of you. Syllabus will be whatever we are discussing till today's lecture. But then again, the most important concepts or the most important topics would be, of course, diodes, MOSFETs as devices, and how do you DC bias the MOSFETs. In other words, for example, the questions that were there in your homework number 4, those will be something that will be very important for this particular exam. Okay. So how do you actually make sure that the VGS of the transistor is something that you want? How do you make sure that the current through the transistor is something that you want, and so on? So how do you basically DC bias the transistor in a circuit? That would be very important, which you have already covered in your homework number 4, and that would be an important topic for the exam. Again, 50 minutes, 10:40 to 11:30 a.m. in the class. And of course, please don't forget to bring your calculators. Okay. Any questions regarding the exam? All right. So what we had discussed in the last lecture is a few different ways to bias the transistor-based circuit. So we have discussed AC coupling, which really means that you just couple the AC signal using a capacitor. So for example, this capacitor lets the AC pass, but it will not let the DC signal pass, right? So in terms of DC, the left hand side and the right hand side of this capacitor can have different DC values. But in terms of AC, they should be same as long as you have designed your pole frequency correctly. So remember that this is a high-pass filter, a capacitor in series, and a resistance in parallel to ground. So that forms a high-pass filter, and the pole frequency of that high-pass filter, if you plot the frequency on the x-axis and let's say transfer function or gain on the y-axis, it would look something like this, right? So at high frequencies, we will get the signal. At lower frequencies, in fact, at 0 frequencies, you will not get any kind of signal. So it's your job as a designer to determine this pole frequency in a way that your intended frequency is, let's say, somewhere over here, so that you do not get any loss because of the filtering action. But if your intended frequency is, let's say, somewhere over here, you'll get a lot of loss just because of this filter, and maybe your circuit will not work properly. So you have to design this filter in a way that this pole frequency is much less than the intended frequency of use. And that is something you have already done in your homework number 3, even though that was an op-amp based problem. So instead of this MOSFET and its load resistance, you had an op-amp, but the circuit was effectively same in your homework number 3. And you already looked into the scenario that you need to design your high-pass filter in a way that it is far away from your intended frequency range. Okay, so that's something we have already discussed in the previous lecture. We have already also discussed a different way of biasing, which is using a degeneration resistance. Now, why do you even use this degeneration resistance? So basically, if I zoom in a little bit more, you have the same kind of circuit again. So let's say your VDD is this point, and you're biasing your gate using this RG1 and RG2 resistors. So that is same as what we had discussed in the previous lecture. This RB, as you'll see, will act as a load of your MOSFET-based amplifier. But there is another resistance over here, which is RS, the source resistance, the resistance connected at the source of the MOSFET. Right? So I'm not talking about the source resistance of the voltage source, which in this case is signified as R signal. So this is V signal, and this is R signal. This RS signifies the resistance that is connected at the source of the MOSFET, the source terminal of the MOSFET. Now, what advantage does it give you? Why would you even place this resistance over here? As we discussed in the last lecture, that the gain will be reduced if you are placing this RS resistance. Gain will become minus RT over RS. And we'll prove that in today's lecture, that how this gain becomes minus RD over RS, instead of the gain being minus GM times RD. So minus Gm times Rd would be the gain of the system. Again, we'll prove this today, that without this Rs resistance, the gain of the systems will be minus Gm times Rd, and that will usually be higher than this minus Rd over Rs. So the absolute value of Gm times Rd will be, in most practical cases, will be much higher than the absolute value of Rd over Rs. So why do you even use this degeneration resistance? It degenerates your gain, it reduces your gain. What is the purpose of using this degeneration resistance? The main reason why you would want to use the degeneration resistance is because with this degeneration resistance, you have a method to stabilize the gain. And why I'm saying that is that, let's just assume that you have some amount of VGS in the system. So you have a gate voltage here, VG, and you have some amount of source voltage here, VS, right? And VG minus VS, that is your VGS of the transistor, that will determine how much current that will flow through the transistor, right? Because from your equation of ID or equation of drain current, you know ID is equal to K over 2 VGS minus VT whole square. K over 2 VGS minus VT, where VT is your threshold voltage, whole square. That's the equation of the current. And that's the current that is flowing through this device. Now imagine that because of some reason, let's say there is some temperature fluctuation, or there is some process variation in the MOSFET, that somebody is using, let's say person A is using a MOSFET, person B is also trying to use a similar MOSFET, but their properties are a little bit different. You have already seen this in your lab 4, that the threshold voltages of the MOSFETs could be different from person to person. The threshold voltage or even the GM of the transistor could be different from person to person, MOSFET to MOSFET. So because of those process variations or temperature fluctuations, let's just assume that this current changes a little bit. And let's just assume initially that this current increases. Let's say whatever current was flowing through this branch, that current increases. If that current increases, what will happen is that the current that is flowing through this Rs resistance, that will also increase, because it's the same current that flows through Rd through the device and then through the Rs. Right? The current has nowhere else to go. KCL, Kirchhoff's current law, states that if this current is coming in, it has to go out of the device in some way. So the current is exactly same in the drain, in the source, and within the device. So the Rs resistance will see a higher amount of current as the current through this device increases. What would that mean? Is that the drop across the Rs resistance will also increase. Right? The current across the resistance is increasing, the drop across the resistance is increasing, because the value of the resistance is same. You apply Ohm's law, which is V equal to IR. If your current is something that increases, if your current is increasing, your voltage is also increasing. Right? That's Ohm's law. So the voltage drop across the Rs resistance will increase as the current through the device increases. So the voltage Vs is basically increasing in that case, because the voltage drop across Rs is equal to Vs. The other terminal of the lower terminal of Rs is connected to ground, which means that the upper terminal's voltage will keep on increasing as your current is increasing through the device. Now what will happen is that because your Vg is fixed, your Vgs will reduce, right? Why I am saying that? Because your Vg is constant, but your Vs is increasing. So Vg minus Vs, which is equal to Vgs, will drop, will reduce. So the Vgs of the device will reduce as soon as the current through the device increases. So what do you get from this equation then? That your Vgs is reducing, so current will reduce and current will come back to the initial value. So if there is any kind of fluctuation in the current of the device, let's say the current of the device increases, the drop across the resistance Rs increases, which means that Vgs reduces, which brings the current back to its initial value. That gives you a stabilization factor. So you can really stabilize the amount of current that is flowing through the device across processes, across temperatures, across many other fluctuations that can happen in the environment. So that's the reason why you would even use this Rs resistance, because that gives you more stabilization in the system. Right? That's the sole purpose that you would use source degeneration resistance like this. Even though it will reduce your gain to minus Rd over Rs, whereas the gain without that resistance was higher, the value of which will be Gm times Rd. The absolute value is Gm times Rd. So that's the reason that you'll ever use this kind of degeneration resistance. That's because this degeneration resistance gives you an inherent negative feedback. You know about negative and positive feedbacks a little bit, right? So negative feedbacks mean that you're trying to, and negative feedbacks, in fact, give you this stabilization factor that if you remember the equations of feedback, that let's say the feed forward gain is A and the feedback gain is beta. So with a negative feedback, you get A divided by 1 plus A times beta. That becomes your gain in a feedback system when the feed forward gain is A and feedback gain is beta. So remember that we have discussed this multiple times in the class in the past, that this is your feed forward path and this is your feedback path, which has a gain of beta. And let's say you just have this as positive and this as negative. So this is the equation of a negative feedback, where you're feeding back part of the output back to the input and feeding it back in with a negative sign, or you're actually subtracting it from the input. So in that case, you get this equation. And you know that if A is very high, what you can do is that you can divide the numerator and denominator with A. And in that case, you'll get 1 divided by 1 over A plus beta. If your A is very high, this term can be neglected. So the gain of the system becomes 1 upon beta. And that is something we had already discussed when we were discussing op amps. What we said is that the gain of the system becomes 1 upon beta if you are having this kind of a negative feedback. And usually this beta network is a network created using resistances. You have already seen examples where you found out beta in your homework number 3 or homework number 2, even your exam number 1, you had to find out beta, the feedback factor, right? And remember that the feedback factor was a function of resistances. And resistances, the ratio of resistances, if the resistances are created using the same batch, if they are fabricated in the same batch, usually the ratio of the resistances remain a constant or very close to a constant, even though the absolute value of the resistance can change. Let's say you have two resistances, RA and RB. The ratio of RA and RB will be very much similar. So for example, let's say your intended value of RA is 100 kilo ohm, intended value of RB is 10 kilo ohm. You want a ratio of 10. But because of process variations, RA could be, let's say, 101 kilo ohm. In that case, you will say RB will most likely also be very close to 10.1 kilo ohm. So that the ratio is always almost constant. So ratios of resistances or ratios of capacitances, they are usually process independent. So even if there is a process variation, you'll see that the ratio will not get affected that much. That's what happens in any kind of real practical resistance and capacitance. So what that means is that even though the feed forward gain A of the system can change drastically. So just assume that the feed forward gain of the system was created using this GM-RD gain of the MOSFET. So GM can change depending on process, depending on temperature. The RD itself can also have many different values. The absolute value can also change depending on process. So GM times RD will change, but the ratio of two resistances, they will not change that much, right, in terms of process variations or temperature fluctuations. So if you can stabilize your gain to be 1 upon beta, that makes your system much more robust, because then instead of this gain 8, you get a gain of 1 upon beta, and that 1 upon beta gain is pretty much stable across temperatures, process, and voltages. The same thing we are seeing here, that instead of a gain of GM times RD, you have a gain of RD divided by RS, and the ratio of resistances is much more robust. That's the only reason, or that's the primary reason that you'll ever have this kind of a degeneration resistance. And the degeneration resistance helps you in stabilizing the current through the device, because as soon as that current increases, VGS drops, and from this equation, you'll see the current has to drop and come back to the same initial value. All right. Questions? It's not a feedback. If you don't have that resistance, there is no feedback at all. If you have that resistance, that gives you the negative feedback. It's an inherent negative feedback through the property of the device, that as soon as the VGS changes, the current through the device will change. So that's an inherent negative feedback. You're not exactly connecting something back to the input side, But because the current depends on the voltage at the input and the voltage at this point, as soon as the voltage at the source changes, your current will change. That's an inherent negative feedback. If you don't have the source resistance, you don't have any feedback. All right. But then again, this is a DC. This is when you are trying to bias your transistor or bias your system in a way that you want a fixed current through the device, you want a fixed voltage VG, you want a fixed voltage VS, and so on, right? So, or effectively you want a fixed current through the device. So that's a DC biasing condition. We did not even talk about AC signals or small signals yet. So in this gain, this RD over RS, that's the small signal gain. If you do not want your small signal gain to suffer, if you do not want your small signal gain to degenerate, there is one way to have best of both worlds. And that is something, again, we discussed in the last lecture, that you bypass this RS resistance with a capacitor. What that will do is that in DC frequencies, at zero frequencies, this capacitor will be open. So you'll get all the advantages of that source degeneration resistance, that you'll get a more robust DC biasing point. Your biasing point will be much more robust. Your current through the device will be much more constant. But at AC frequencies, this capacitor will be a short. So for AC frequencies, the effect of this RS resistance will not even be there. So you'll get your gain of GM times RT. But at the same time, you have this negative feedback at DC frequencies, which means that your circuit will be much more robust. So you get best of both worlds by including a bypass capacitor here. You do not lose on gain, but at the same time, your biasing is much better. Question?
So your DC point would be a lot more stable.
Yes, exactly. So the current will not fluctuate, because let's say which temperature the current can fluctuate, could have fluctuated. But if you include this degeneration resistance, even if the temperature fluctuates, the current will not fluctuate. Okay, so the DC point will be much more stable, it will be much more robust. But at the same time, you had this trade-off, you had this disadvantage that your gain was reducing. But just by placing this bypass capacitance, you get back the gain to be equal to GM times RD, because at AC frequencies, at high frequencies, the capacitor shorts the resistance to ground, right? You have a parallel short to this resistance. Okay, so this is having the best of both worlds, that your DC point is much more stable, but your AC gain is also high. All right. So with that background in mind, in today's lecture, what we'll start doing is the AC analysis of the devices. Till now, what we have looked at is just the DC analysis, that what is the current through the device, what is the VGS of the device, what is the voltage at each point at the circuit. Those are all DC voltages, right? We never talked about what is the AC small signal swing till now. We have not talked about AC small signal at all till now. Your homework number 4, that talks about only the DC biasing points. It does not talk about the AC small signals yet. Now, why we talked about the DC biasing points first? Because remember, we discussed VTC, voltage transfer characteristics, and I keep on drawing this over and over again, but that is probably the most important plot, the most important graph that we'll encounter in this particular class. Because you can expect a gain only in this region. You do not expect a gain over here. You do not expect a gain over here. So it's of paramount importance that you first create and you first fix your DC biasing points to be somewhere over here, so that you can expect gain. Now, what we did in the previous 2 lectures, what we did in the homework 4 is that we made sure that the DC biasing point is in a region where you expect gain. And what is this region? This region has to be saturation region or active region of the MOSFET. If the MOSFET is in triode, if the MOSFET is in cutoff, you do not expect any gain out of it. You expect the gain out of the MOSFET only if it is in saturation or active. Like those are just the same region but different names. Okay, so now assuming that you have biased it correctly, you have biased it in the middle of the VTC, you have biased the MOSFET in the active region or in the saturation region, assuming that, we'll do our AC analysis. We'll try to find out what will be the gain of the system. To do that, you would have to do a Norton or Thevenin equivalent circuit of the MOSFET. And that is something, again, we have discussed before, that this is the linear equivalent circuit or the AC small signal equivalent circuit of a MOSFET, that you have this as the gate terminal, you have this as the source terminal, and you have that as the drain terminal. And this is something we have discussed in the past, that this is very similar to your op-amp's AC small signal linear equivalent circuit. That if you apply a voltage of VGS, you'll see a current of GM times VGS at the drain terminal. So it is a voltage controlled voltage source. Voltage controlled current source in this case, because we are showing a current. In the op-amp scenario, you could have also shown a voltage controlled voltage source or a voltage controlled current source. If you had shown a voltage controlled voltage source, you would have had a series resistance with that. But in this case, we are showing a voltage controlled current source, so we'll have a parallel resistance to go with that. And that parallel resistance is the output resistance of the MOSFET itself, which is nothing but RO. And you know what is the value of RO? RO is equal to 1 upon lambda ID, where lambda is the channel length modulation parameter and ID is the current flowing through the MOSFET when you are fixing the DC bias points. All right. So you already again know about these different things, that okay, if you connect a voltage, non-ideal voltage source at the input, let's say you connect a VS voltage source and you have this RS as the non-ideality of that voltage source. So of course there would be a voltage division between this RS resistance and the input resistance of the MOSFET. Right? There would be some kind of a voltage division between these two. We again studied this when we were doing our homework number 2, for example. Again, at the output side, you have this RO resistance of the MOSFET, output resistance of the MOSFET, but in parallel, you can connect another load resistance to that MOSFET, because this is internal to the MOSFET. You have to connect an external load resistance to see any voltage value across it. Right? So you do not have, even though this resistance exists, you do not have access to this R out of the MOSFET. This is not a physical resistance across which you can measure the voltage or the current. So you have to connect a load resistance, and then this RO and RL will come in parallel. Right? So again, you know about all these things, that when RO and RL comes in parallel, you have to consider the effect of RO and RL together, and then you'll see a current division between RO and RL. So your gain will reduce again a little bit. These are some things that you have learned in the past, that there will be a voltage division at the input side, there will be a current division at the output side, and your overall gain will reduce a little bit. And that's something we're writing over here, that if you're at the output side, your equivalent resistance will be RO. This is RO in parallel with RL. So RO in parallel with RL, that is your RL equivalent. Your voltage gain, let's call it AVT, and let's call it let's define it as the voltage at this point as VO, output voltage, and the voltage between the gate and source terminal, let's call it V input at the terminals. So VIT, V input at the terminals. Now you know that gain will be GM times R equivalent. Again, why? This is something we have proved before, that the gain, current at the output is GM times the voltage at the input. So current at the output, I out, is GM times the voltage at the input, and voltage at the input is VIT in this case. What would be the voltage at the output? Voltage at the output would be this current at the output multiplied with the effective output resistance, and effective output resistance in this case is RO in parallel with RL. So the current that comes out, which is equal to IO, that is equal to GM times VIT. GM times VIT is the current, and that gets divided into two resistances. But then again, the voltage that will develop across both of those resistances will be VO, which will be equal to IO times RL equivalent. Correct? If that is true, what would be your VO divided by VIT? VO divided by VIT will be GM times RL equivalent, right? Because IO is GM times VIT, VO is IO times RL equivalent. So you can write VO is equal to GM times VIT times RL equivalent. So VO divided by VIT will just be GM times RL equivalent. So your voltage gain, if we define it in this way, that the voltage gain is VO divided by VIT, that will be GM times R equivalent. But the overall voltage gain, the output voltage divided by the input voltage, that's your overall voltage gain in the entire system. That overall voltage gain in the entire system, let's call it AVS, the voltage gain as compared to the source voltage, VS. That's why you are calling it AVS. That is VO divided by VS. So what is the only difference? The only difference is that at the input side, you'll see a voltage difference, or you'll see a voltage division between RS and this RI, and that will create your VIT. So VO over VS is basically VO over VIT multiplied with VIT over VS. Right? VO divided by VS is equal to VO divided by VIT multiplied with VIT divided by VS. What is VIT divided by VS? That's this voltage division term. RIT or R input divided by R input plus RS. So you see this voltage division at the input side, and that will be something that will be reflected in your overall system level voltage gain. So again, this is nothing new, same as what you have studied before in the course. Okay, now, and this is basically telling you that let's say if you had an ideal voltage source which has RS is equal to 0, in that case, this RIT divided by RIT plus RS, this term will be equal to 1 because RS is equal to 0, so you can neglect this RS. Then it will be RIT divided by RIT, which is equal to 1, right? So there will be no effect of that voltage division if the voltage source at the input is ideal. Now, what is the overall gain in the entire circuit? Assuming that the voltage source is ideal, in that case, it will just be equal to AVT, and AVT is something that you have found out before. AVT is equal to GM times RL equivalent. What is RL equivalent? RL equivalent is RO in parallel with RL. RO in parallel with RL. If your RO, if the output resistance of the transistor is much more than the load resistance that you have connected, then RO in parallel with RL will equivalently be only be equal to RL when RO is much larger than RL. If RO is much larger than RL, the RL equivalent term will effectively be equal to RL. So your gain will be equal to GM times RL. So this is the absolute value of the gain in the transistor-based circuits, and this is what we talked about before, that in this particular system, if this RS resistance is not there, the gain of the system is minus GM times RT. The absolute value of the gain is GM times RT. If you don't consider the negative sign only means that there is a inversion of the phase. That if you at your input side, if the sine wave looks like this, at the output side, the sine wave would look like that. Right? So there will be a 180-degree phase difference. That's all the negative sign means. The GM times RT is basically what you have proved over here. We were calling it RL, or the load resistance. In this case, the load resistance is basically this RT, which is connected at the drain. The drain is your output terminal for the MOSFET here, right? So whatever resistance you have connected at the output terminal, that would be your load resistance. In this case, the load resistance is RT. That's why you are calling the gain as GM times RT. And that's what something we proved over here, that the gain is GM times RL. If RL is RT, then the gain becomes GM times RT. But what is interesting is that whenever you have an unbypassed source resistance RS, then we'll try to find out what would be the gain of the system. Let's say you have the unbypassed source resistance. So you have this MOSFET. Okay, so let's say you have this MOSFET over here. This is your MOSFET. And at the source terminal, you are connecting this RS resistance. At the drain terminal, let's say, just for simplicity initially, let's not connect anything at the drain terminal. Okay, let's just try to find out what would be the gain of this particular system. And in this case, you can again draw the linear equivalent model of the MOSFET. The linear equivalent model would look like this. That you have a gate voltage. You're developing a gate to source voltage because of that gate voltage. The source terminal, at the source terminal, which is over here, you're connecting this resistance, right? So this is your source terminal. This is your gate terminal. And this is the voltage VGS across the source and the gate terminals. The current that is flowing through the MOSFET is GM times VGS. Right? That's just from definition of GM and VGS and output current. That the transconductance multiplied with input voltage, that gives you output current. That's just the definition of output current. So GM times VGS is your output current in the MOSFET. And let's say you have connected this drain terminal to a AC ground. So this is written as VD to be equal to 0. But remember that this is an AC ground, which means that this could be your VDD. This is in fact your VDD, because without this point, if this point is ground and this point is also ground, can there be any current flow from ground to ground? No, right? So this point is in fact a VDD, which is an AC ground. Why do we call it the VDD as an AC ground? That's because VDD does not have any AC fluctuation. The supply does not have any AC fluctuation. Supply is a constant DC voltage. If it is a constant DC voltage, the AC voltage at that point is 0, which means that this can be considered as an AC ground. So that's why we have connected it to ground when we are doing the AC analysis. In terms of DC, of course, you'll see that there will be a current flow from VDD to ground. But in terms of AC analysis, you can consider this point to be same as the other ground. All right. So your VD at this point, the AC voltage VD at the drain terminal is equal to 0. The AC voltage VS at the source terminal is equal to ID times RS1. ID is the current that is flowing through the drain or flowing through the device. That is equal to GM times VGS. And GM times VGS times RS1 is the voltage at the source terminal. Correct? Again, Ohm's law. Voltage equal to current multiplied with resistance. So what would be your VGS? VGS is VG minus VS. Gate to source voltage is the gate voltage minus the source voltage. So VGS is equal to VG minus GM times RS1 times VGS. So now you see you have VGS on the left side. You also have a VGS term on the right hand side. You can take this entire VGS, all the VGS terms on the left hand side of the equation, and you can write VGS times 1 plus GM times RS. VGS multiplied with 1 plus GM times RS, that will be equal to VG. So what would be your VGS? Your VGS will be equal to VG divided by 1 plus GM times RS1. That's your VGS. VG divided by 1 plus GM times RS1 becomes your VGS. What would be your ID? ID is the drain current through the MOSFET. That would be equal to GM times VGS. Again, just from definition, that the output drain current is equal to GM times the gate to source voltage. Again, see that we are only talking about AC voltages and AC currents over here, because we are doing an AC analysis from today's class onwards. And the purpose of doing an AC analysis is that you want to know what would be the AC gain of the system. Till the last lecture, we only discussed about DC, but from today's lecture onwards, we are also starting discussions on AC analysis. So all these terms are AC terms. Okay, so you can assume that there is a sine wave at the input, there is a sine wave current flowing through the device, and there is a sine wave voltage across this RS1 resistance, and so on. So everything is AC in today's discussion. So ID is equal to GM times VGS. That would be equal to GM divided by 1 plus GM times RS1 times VG, because you already know VGS looks like this. This is your equation of VGS. You just put this equation of VGS over here, and you find ID to be equal to GM divided by 1 plus GM RS1 times VG. So this also gives you some sense that, okay, there is a degeneration factor of GM times RS1, right? The current ID, if there was no resistance over here, if let's just assume that there is no resistance here, right? If this resistance is not present, then your VG will be equal to VGS, because your source will be grounded if this resistance is not present. So VG will be equal to VGS, and the current through the device, ID, will be equal to GM times VGS, or you can write it GM times VG. That would have been the current through the device if there were no degeneration resistance. If this resistance were not present, then ID would have been GM times VG. Now with in presence of the degeneration resistance, ID is equal to GM times VG, but that is divided by this factor 1 plus GM-RS1. That's what we have been talking about in the previous lecture as well, that because of this degeneration resistance, the AC quantities at the output, the AC current at the output, or the AC voltage at the output will be divided by this 1 plus GM-RS1 factor. That's the meaning of degeneration, that you are degenerating the output current or the output voltage, in fact, the overall gain of the system by a factor of 1 plus GM-RS1. That's the amount of degeneration you have. Okay. So what you can, from this particular equation, you can also represent it in the form of ID is equal to capital GM times VG. ID is equal to capital GM times VG, and your capital GM will basically be this GM divided by 1 plus GM-RS1. So this is your modified GM. Ideally, without the existence of that source resistance, your GM, this capital GM would be equal to small gm. Because see, over here I have written ID equal to capital GM, small lowercase gm times VG. Here I am writing ID equal to uppercase gm times VG, and that uppercase gm does not mean it's a DC quantity, it just means it's the modified value of gm in this case. That's how usually it is represented in the books as well. You will see that this is the modified value of gm in presence of that degeneration resistance. And that modified value of the GM is original GM divided by 1 plus GM-RS1. So you get a degeneration in terms of the GM, you get a degeneration eventually in terms of the ID current, and eventually you get degeneration at the output voltage as well as the gain. All right. So that's what the final conclusion is here, that the capital GM is always less than equal to small gm. That's why we are calling it a degenerated resistance or the degeneration resistance. And this is a circuit which has the degeneration resistance. Questions? This is the modified GM, the capital GM that I'm defining. Top left. Yes. So capital GM is basically equal to ID divided by, so whatever current you are seeing at the output divided by whatever voltage you have applied between the gate and source, right? Or the small GM is equal to ID divided by VGS. That's just from definition. And that small GM is equal to K times V of V equal to square root of 2 times ID divided by V of V, and then you had those three equations, right? K times V of V. The other form of the equation is square root of twice beta times ID, and that will be equal to twice ID divided by V of V. So those were the three equations that you had for GM. This is just for the small GM. And small GM is the property of the transistor, that what is the ID going through the transistor and what is the gate to source voltage of the transistor. The small GM is just a property of the transistor. It has nothing to do with the circuit. So you can have hundreds of resistances, capacitances, inductances in the circuit. This capital GM is something that we are defining for the circuit, that what is the effective GM that you see at the circuit if you have your output current of the circuit as ID and input voltage of the circuit as, let's say, VIP or VG in this case. The little case, the lowercase gm and the uppercase gm will be equal only if the degeneration resistance is not there. They will be equal when the degeneration resistance is not there. And let me again rephrase it and try to explain it in a different way. The smaller case GM, the lower case GM, is basically the transconductance of the MOSFET. Let's say you just bought a MOSFET from the market. That has certain properties, right? That you apply your VGS at the gate and source of the MOSFET, and then you get some amount of current. That's just a property of the MOSFET. And this GM is just the property of the MOSFET. That's it. But a circuit can have hundreds of resistances. A circuit can have hundreds of capacitances, inductors. And in that case, we'll define this uppercase GM or capital GM, and we'll say that what is the capital GM? That capital GM is the ID of the circuit. So the AC, or let's say, let's not even call it ID. Let's call it I out, because that would be the correct thing to do. So I out of the circuit divided by V in of the circuit. So I out of the circuit, or basically del I out of the circuit divided by del V in of the circuit, that gives you the capital GM. That's how we'll define the capital GM. Capital GM is the transconductance of the circuit, not for the MOSFET. And the transconductance of the circuit can be defined from the transconductance of the MOSFET. In this scenario, the transconductance of the circuit would be the AC current that is flowing through the MOSFET and the degeneration resistance divided by the change in the AC voltage that you have applied at the gate terminal. But the voltage that you apply at the gate terminal is not same as the VGS. Because of the degeneration, the VGS will be different from the gate voltage. So capital GM is the transconductance of the entire system, whereas small gm is the transconductance of just the MOSFET. Okay, so if you can remember that, I think the rest of the discussion will become very clear. Questions?
The beta that you defined.
Yeah.
Oh,
here.
That beta, that's also beta is equal to K.
Oh, sorry. Yeah, I should write K, because yeah, when you discuss this in class, we call this K. So square root of twice K times ID, or 2 times ID divided by VOV, or K times VOV. All of them represent this small gm, which is the transconductance of the MOSFET. So lowercase gm is the transconductance of the MOSFET, uppercase gm is the transconductance of the entire system. Okay, I hope that makes it clear. Just try to remember that, and we'll solve multiple circuits that will give you a better idea about the lowercase gm and the uppercase gm. But in this case, with the degeneration present, I guess the uppercase gm is clear that, okay, you found out what would be your ID. Your ID is this lowercase gm divided by 1 plus gm times RS1 times VG. And VGS is the voltage that you have applied to the system. ID is the current that you're getting out of the system. So this becomes the transconductance of the entire system. And the transconductance of the entire system is a degenerated version of the original transconductance of the MOSFET. All right. So let's try to solve an example, and then we'll stop for today's lecture. We have probably 6 minutes, and that should be enough time to solve this example. Okay. So in this example, your VDD is 10 volts. The ID is said to be 1 milliampere. The drain voltage is 5 volts. So at this point, you're trying to develop 5 volts. The source voltage is 2.9 volt. That is at this point. And this resistance is 2.9 kilo ohms, right? So if the current flowing through it is 1 milliampere, of course, the voltage developed across the 2.9 kilo ohm resistance will be 2.9 volts. VG is 4 volts. So that's the voltage that you're trying to create here. And V overdrive, in this case, is 0.25 volts. GM is 8 milliampere per volt. Now, if you draw this AC equivalent circuit in this case, what do you have? You have VS, you have the RS, which is the source resistance, which is the source resistance over here. This 40 kilo ohm seems to be a typo. Here it was mentioned at 10 kilo ohm. Let's see how the calculation goes, and then we can decide which value is to take, 10 kilo ohm or 40 kilo ohm. It's just that, yeah, one would be the correct one, the other one would be the incorrect one. That's fine. So C1, you can assume that because this is a coupling capacitance, this is a short at your AC frequencies of interest. So this is a short. Then you have this RG2 and RG1, and they will come in parallel when you are considering the AC equivalent circuit. Why would they come in parallel? Because again, RG2 goes to ground, RG1 goes to VDD, which is a virtual ground, AC ground, right? So RG2 and RG1, they are in parallel and they are both connected to a virtual AC ground. This point goes to the gate of the MOSFET. You have a 2.9 kilo ohm resistance connected at source, and you have 5 kilo ohm resistance connected at the drain. Again, you have a coupling capacitance at the output and your load is 20 kilo ohms. At the input side, you have a parallel combination of RG1 and RG2. And let's say RG1 was, I think, 600 kilo ohms. RG2 was 400 kilo ohms. So the parallel combination of 600 and 400, that gives you 240 kilo ohms. That's your resistance connected at the gate. The RL equivalent, the load resistance connected at the gate terminal, that is RL equivalent, that would be equal to RD in parallel with RL. What is RD? RD is this RD connected to, again, an AC ground, which is a VDD. And through this shorted C3, this capacitance, you are also connecting it to RL, which goes to ground again. So RD in parallel with RL, which is 5K in parallel with 20K, which will be equal to 4 kilo ohms. So 4 kilo ohms is your RL equivalent. What are we ignoring here in the RL equivalent is the output resistance of the MOSFET. So ideally, it should have been RD in parallel with RL in parallel with RO. Because remember that the AC equivalent circuit of the MOSFET, which we discussed in the past, maybe it's better if we go back to over here. So the AC equivalent circuit of the MOSFET was this current source in parallel with its own resistance, right? RO resistance, which is connected to source, in between drain and source. And at the drain terminal, you can connect multiple other resistances. So what is happening here is that at the drain terminal, you have connected RD to ground, you have connected RL to ground. So all three of these resistances are coming in parallel, RD, RL, and RO. But since RO is much, much higher, RO is, let's say, 100 kilo ohm or so. If RO is 100 kilo, and in this case, you can even ignore RO. If you can even, the question may have also mentioned that RO is infinite. You can assume RO is infinite. That could be there in the question in your exam, or let's say in later exams, that RO is infinitely high. In that case, RD in parallel with RL in parallel with RO will just be this parallel combination of 5K and 20K, which will be equal to 4K. Okay. So what would be your GM? The GM of this case, in this case, because you have this source regeneration resistance, because of the presence of this source regeneration resistance, your capital GM will be small gm divided by 1 plus GMRS. That's what we found out in the previous calculation, that your capital GM is equal to small gm divided by 1 plus GMRS when there is a source regeneration resistance present. So your capital GM equal to 8 milliampere per volt divided by 1 plus 8 times 2.9 kilo ohms. So that gives you some value of 0.33 milliampere per volt. What is interesting there is that you can also just calculate 1 upon RS1. So this is GM divided by 1 plus GMRS1. So let's just divide the numerator and denominator with GM. You get 1 divided by 1 over GM plus RS1. And in most cases, you'll see that it's almost equal to this 1 upon RS1. It can be approximated as 1 upon RS1, which will be 0.345 milliampere per volt, whereas the exact value is 0.33 milliampere per volt. So if you just want a ballpark number, 1 upon RS1 is also fine. Now, what would be your voltage gain? Voltage gain would be minus GM times R equivalent. You already know what is your capital GM. You already know what is your R equivalent. The multiplication of those two will give you the gain 1.32. Or if you just approximate this to be minus R equivalent divided by RS1, that gives you minus 1.38, which is very similar to the original gain of minus 1.32. So what I'm saying is that instead of considering GM to be GM divided by 1 plus GMRS1, you can also consider it to be just 1 upon RS1, and that gives you almost similar values. So now, what that means is that if your original without the source rejection resistance, if your gain was GM times RD, what we are saying is that instead of this small GM, if you consider a capital GM of 1 upon RS1, that would also be very similar to the gain of the source regenerated circuit. So you replace GM with 1 upon RS1, you get minus RD divided by RS1. That's what we said in the beginning, that with source regeneration, your effective gain becomes minus RD divided by RS. So whatever connected at the drain. So I'm calling it RD, but it's effectively RL equivalent because there are other resistances connected at the drain terminal as well. So you have the RD resistance connected at the drain, but you also have the RL connected at the drain. So it's basically RL equivalent that you are looking at. And that minus RL equivalent divided by RS1, that gives you minus 1.38, whereas the exact calculation gives you minus 1.32. And finally, if you want to consider the effect of this RS and the gate resistances, so there will be a voltage division between the gate resistances or the input resistance of the MOSFET and that RS. So you know that the parallel combination of RG1 and RG2 was 240 kilo ohms, whereas this RS was 40 kilo ohms. So it will be a voltage division of 240 and 40. So 240 divided by 240 plus 40. So this will also be very close to 1. So maybe about 0.9 or something. So finally your ABS will be this minus 1.14 volts per volt. So we'll stop here. Let me know if you have any kind of question. So this is in fact 40 kilo ohms. This is not 10 kilo ohms, so this should be 40. Okay.